Have you ever wondered if space and time, two seemingly separate entities, could actually be intertwined? Today, we are going to dive deep into the fascinating concept of space-time. Imagine someone asking you to define your exact position. You could give your X, Y, and Z coordinates, pinpointing your literal place in space. This three-dimensional system is what we use globally to describe where an object resides. But what happens when we introduce a fourth dimension, time? This is the foundation of the concept of space-time. We perceive time as a constant entity in our everyday lives, one that unfolds regardless of anything else. Whether you're in New York or Mumbai, time ticks at the same pace and in the same direction, forward. This is how time is characterized in classical physics. But this definition has its limitations, and there are many phenomena that the principles of classical physics cannot explain. This is where quantum mechanics come in. Famed physicists Albert Einstein and Max Planck are considered the pioneers of this branch of physics. As early as 1905, Einstein proposed a now widely popular theory that the speed of light is independent of the motion of all observers, and that space and time are interconnected in a singular continuum. This theory, now a cornerstone of modern and quantum physics, is known as Einstein's special theory of relativity. Einstein's idea of a singular continuum where space and time are interwoven is what we call space-time. According to this theory, time, traditionally considered an independent entity according to the principles of classical physics, is affected when a body moves through space. This happens because, according to the theory, time and space are connected and are part of a singular continuum. Space-time. One of the most popular examples of this is the hypothetical scenario where if you were to move incredibly fast, nearing the speed of light, time would slow down for you. Furthermore, Einstein hypothesized that observers moving relative to each other would not agree on the synchronization of simultaneous events. Put simply, if one observer states that they observed two given events occurring at the same time, another observer, moving relative to the first, would disagree, stating those events happened at different moments. After bringing his ideas about space-time and the indissoluble link between space and time to the world, Einstein continued to work on his theory, studying how massive objects impact the fabric of space-time and later introducing gravity into the mix. Consequently, the general theory of relativity was published in 1915, a decade after the special theory of relativity. Traditionally, gravity has been defined according to Sir Isaac Newton's three laws of motion, a force of attraction that exists between two bodies, no matter how small or massive they are. You, watching this video, are being pulled towards the center of the Earth. This is what prevents you from floating in the air. However, according to the general theory of relativity, all objects exist in the space-time continuum and distort the space-time around them. In this discussion, we've delved into the concept of space-time, the theories of renowned physicist Albert Einstein, and how these ideas revolutionized our understanding of space, time, and gravity. We've explored how time, traditionally seen as constant and unchanging, can actually be affected by movement through space. We've also looked at how gravity, as defined by the general theory of relativity, is a distortion of the space-time continuum by objects within it. A truly mind-bending concept that pushes the boundaries of our understanding.